Hello, good morning to everybody. Let's first check if you all hear me okay, if the image is also okay.
Good morning, Georgina. I can hear you quite well.
Thanks, Jaume. Good morning. Well, I'm going to introduce a little bit Jaume and myself while we wait for 9 o'clock. I'm Georgina Comas. I'm the Deputy CEO here in TMCOMAS. And I want to introduce now Jaume Nin, who's our PhD technical director, and also he's in charge for the research and R&D projects in the company. Jaume is a PhD in thermal spray, so you are in the best place to know about thermal spray and laser cladding applications. Today we're going to speak about this, about thermal spray and laser cladding applications and we're going to compare both techniques, and we'll see which application is better for one or for the other one, and we'll see some real examples of application. If you need more information about thermal spray or laser cladding techniques, you can visit our YouTube channel, where you can find webinars which are only of thermal spray or only about laser cladding applications, and many other interesting webinars are there. I want to also explain you that in November we'll do another webinar, which is called which will talk about Babbitt bearings and all the techniques to produce it, and different examples of reparation and construction of Babbitt bearings. And after that, we'll stop the webinars until next year. Maybe in February we will start again with a new group of webinars, for applications like extruder equipment or like compressor equipment, and what kind of reparations or pieces we can do in these machines. So for me, that's all. Jaume, it's time for you.
Thank you very much, Georgina, for this nice presentation. Let's wait for 1 minute, something like that, to see if someone else is joining us today. But let me first reintroduce myself. I am the R&D, the Research and Development and Technical Director for TMCOMAS since 14 years ago. I am chemist, then I make a PhD in material science, especially in thermal spray coatings in the University of Barcelona. I make some stages in Canada, in Finland during my PhD. And then I became a member of TMCOMAS team. And during my first years here, I also make studies of welding engineering. So I am a European welding engineer. I have also a lot of background in brazing welding, brazing joining technologies. And after being here for 15 years, I have learned a lot of mechanical, and especially how to repair rotors and several pieces, because here in COMAS we are a mechanical workshop who deals with the reparation of several components for oil and gas and petrochemical companies around Europe, and also now starting around the globe. So I think that there were some problems, but if no one else is complaining, and if you can hear me well, I will proceed with my presentation today. So one thing, if someone of you has any question during my presentation, you can use the chat option. Although from my desktop it's difficult sometimes to see. I'm very concentrated in what I'm saying, so it's difficult for me to see your questions. There's only a small red light that is turning on when someone is chatting something. My apologies if you send me some questions and I am not able to see it, but afterwards, at the end, I will try to check the chat panel to see if someone has told me something. Okay, so okay, let's share my my presentation. Hold on. Yeah, okay. Let's share the screen then. Okay. Fine. So theoretically, now you are able to see my screen. And okay, so the title of today's webinar is Application by Plasma versus Application by Laser Cladding. Well, here we have committed a small mistake due to our way of speaking here in Spain. We call plasma to all thermal spray coatings. So frankly speaking, the application, the title of my webinar should have been Application by Thermal Spraying versus Application by Laser Cladding, okay? So what we are going to do today here is to compare more or less the benefits of both techniques, and then some use cases will be shown just to see how we are managing to choose between thermal spray or laser cladding. So the index of this presentation of this webinar should be, or will be, then first, what is thermal spray, then what is laser cladding, and then a brief comparison between these two technologies, and then use case at the end, questions. If someone has missed the previous webinars, all of them are available in our website, in the network. So you can download the English version or the Spanish version to learn more about thermal spray specific webinar, or to hear the complete webinar of laser cladding. And because before doing this comparison webinar, we have done some specific webinars for thermal spray and laser cladding. All of them are available in our website. So let's start first with thermal spray. What do we understand by thermal spray? Maybe most of you know it's a family of technologies that has something in common. Those technologies allows us to obtain thin coatings, I would say from 30 microns to 1 millimeter more or less, even that it's possible to go further than that. We may talk it about later, but the most standard thickness is 0.3, I would say 0.02, 200 microns, 300 microns, and in special applications, 1 millimeter, 2 or more. So those technologies allows us to obtain thin coatings from a material in the form of a powder normally, or also some of wire, but normally we work with powders, thanks to the combined action of heat treatment and acceleration that takes place in the gun. The gun is a device that it can be moved by hand, by robot, or by a mechanical jig that will move this spray of molten or semi-molten particles that will be accelerated because of the expansion of the gases, or because of the pressure of the input gases, to create a particle, to create a spray of hundreds of or millions of tiny particles that will go into the surface to be coated. So at the end, it's like painting with electrospray paint. So we are applying layer by layer onto the substrate until having enough material for the application, right? So there is, we should have some kinetic and thermal energy available in the gun to melt and accelerate the feedstock material, whether it be powder or wire. this energy has to interact with the feedstock material, and all of this, it took place in the gun and during the flight of the particles to the substrate. And then the last step is the interaction of the spray particles with the substrate. Okay, it's very important also how they interact with the substrate to achieve a good bonding, a low porosity, or the properties that we are looking for. So at the end, we will have a coating that is mechanically adhered to the substrate. There's no diffusion, there's no welding, it's just mechanical adhesion to the substrate. And that will look more or less like these coatings. Depending on the material and depending on the nature of the coating, it will have a certain look in the microscope, but at the end, all these coatings more or less have the same thing, which is a lot of tiny droplets that we call splat that have been deposited one over the other. Some microporosity, some maybe melted particles, some oxide, depending on the atmosphere. If the thermal spray is done in vacuum, then we don't have oxide, so we have a pure coating. But normally we spray in open atmosphere, so there is some certain of oxidation, depending on the technique and so on. But in general speaking, there is some oxidation in the coating, and at the end we have some thickness. Okay. All these coatings have to be done in a soundproof booth with the ventilation, the extraction because of the fumes and burn gases. So these coatings we are performing in closed, especially design booth. It's also possible to spray in situ, but in those cases, some natural ventilation or some extraction should take place. Otherwise, it can be quite foggy. And it's what I told you. It's like painting. We here can be different processes, different flames, different parts to be coated, and in all of them, we can see that there is a flame, there is a stream of particles that will hit the part to be coated. Okay, we can do inner coatings, we can do exterior or external surfaces. Okay, we can work. We usually work with robots, but also we can work with some mechanical jig that is moving in next direction the gun. Okay. So up to here, a brief summary of thermal spray. Now, laser cladding. And now we are not talking anymore of coatings that are mechanically adhered to the substrate, but we will talk of welding. So laser cladding is a kind of welding, but with cladding, but with laser. Sorry. So in this case, there will be a real diffusion of the layer of the top coat to the substrate. So there will be a heat input. It will be some dilution. It will be some mechanical distortion, like in a normal welding. And that's the key of laser cladding. Laser cladding is that welding technology with the lowest heat input to the part. That means that we will have the lowest dilution rate, we will have the lowest mechanical warpage, the lowest mechanical distortion of the parts. And this is very important for us, okay? Because we are able to clad parts that are cladding with arc welding. It will be impossible because they will distort. And so it's not possible to weld these parts with conventional welding techniques. Okay, so at the end we have a laser beam which is focused by some optics And here in blue, in blue shape, we can see the laser beam that has been focused in the surface. With laser cladding, we will concentrate all the power of the laser in the surface. We are not interested in cutting, not in welding, where in these technologies we have more penetration. We kept the penetration in the surface. So as long as we are in the surface, the dilution will be quite low. And here we have the laser beam that has been focused in the surface, and also we have to focus in the same spot the feedstock material. It can be powder or it can be wire. In TMCOMAS, we have powder devices, so we are working always with powder. So we focus the feeding of the powder in the same place, in the same spot, in the top surface of the base material, as together with laser beam. So at the end we have a melt pool here, and then the cladding head will move quite fast because we have a lot of power. So the welding speed, the cladding speed, we can achieve is up to 1.5 meters per minute. So it's quite fast. Okay, so this movement is done by a robot or by a CNC machine, and at the end we will achieve a very nice and well-positioned welding track that will cover all the repair area. Okay, so all these three pictures here are different views of the laser cladding principle, but in all of them you can see that the focus of the powder it has to be the same that the focus of the laser beam. Okay, so how does it look like a laser cladding clad? So like that. You can see here that's the gray color shape is the welding track cut in a transversal way in a microscope. So here we have the cladding material, and here is the base material. And as we can see, the dilution is even zero. It's not zero. Maybe we have 1-2% of dilution, 3%, 4%. Even if we have a 5%, it's a very nice result in comparison with other techniques. Okay, so at the end we will have some overlapping of the individual tracks to create a cladding track, a cladding weld, maybe 1 meter length, 2 meter length, whatever. No. So at the end we have a lot of overlap cladding bits like that, and as you can see here, it's not. Maybe it's not possible to see a lot, but as you can see here, the dilution is almost zero. Here, a big magnification of three overlaps welding track: the first one, the second one, and the third one. And here the dilution is almost zero. And here, maybe because of some heat input, some heat accumulation, it's something else, something a bit more. But it's a very nice microscopy. So the cladding operations takes place into a closed space because of the safety. Radio radiation is very harmful for the eye, so everything has to be kept in a closed space with some security in the doors. In case someone opens the doors, everything is stopped to avoid workers and technicians injuries. Okay. In our case, we have two ways of moving the cladding head. This is the cladding head. We are moving it with a robot, for example, to repair this compressor rotor, and we can also use the CNC machine for smaller parts. Okay. Here we can see how it's the welding. This is the nozzle head, and here we have three small holes where the powder is fed into the melt pool, which takes place in the surface of the part to be repaired. In this case, it's a rotor. It's a compressor rotor shaft that we are cladding this area here. or here it is a long piston rod. Okay. So now, after having summarized the thermal spray and laser cladding technologies, I will make a kind of comparison between the technologies. It's a comparison that has been done by me, so it's not anything extracted from internet or from any technical paper. Is how I look them. So it's my way of seeing them. Maybe someone else has another way of seeing, but I would like to emphasize something. For example, and in the central row, we have the thermal spray, and in the right side, we have the laser cladding. So the adhesion mechanism in thermal spray is mechanical, while in laser cladding is chemical. It's a real weld, so we have some diffusion welding. Heat input in thermal spray technologies is minimum because the flames are produced in the gun, not over the substrate, so the heat input is minimum, while in laser cladding is low, is the lowest of all the welding technologies. Feedstock material versatility. In thermal spray is higher, while in laser cladding is medium to low. And that's because in laser cladding is a welding, and we cannot weld ceramics, for example. We can braze them, but we cannot weld them. So all the ceramics are just sprayed by thermal spray and not applied by laser cladding. Base material effects. So yes, in thermal spray is low. There is no welding, so the weldability is not important for us in thermal spray. So the effect of the different material in base material is not important in thermal spray. We can spray over copper, over aluminium, over titanium, steel, stainless steel, Inconel, Hastelloy, whatever, no? While in laser cladding, the weldability is very important because we have to perform a weld, and the weldability is mandatory to have a look at it. The ease of application in thermal spray is high because we don't have such spatial restriction as in laser cladding. Laser cladding, the cladding head is bigger, is cumbersome, so sometimes it's difficult to access to the area where we want to place the coating. While in thermal spray is more easy. The guns are smaller. You can spray by hand. So it's the ease of application is higher in thermal spray. Application cost. In thermal spray is medium to high. There is some technologies that are quite cheap, while others are tremendously expensive, like vacuum plasma spray or cold spray or advanced HVOF or APS. But in laser cladding, generally speaking, the costs are higher. The laser source cost is higher. The optics, the cladding head, the fiber. But well, it can be in some particular cases it can be more or less impaired. The possibility to apply coatings in situ in thermal spray is possible. We can spray a lot of boiler tubes, for example. Not with all techniques, but with some techniques that are more portable, so it's possible. While in laser, it's possible also, but it takes more. It's more complicated. You have to take a laser, a robot for the movement. The fiber can be it cannot be very long, so you have a restriction from the laser source to the cladding head. So it's more complex to work in situ with the laser, okay? Inner coatings, in thermal spray is available 100%. In TMCOMAS we have inner guns for plasma spray, flame spray, and HVOF spraying, which is not very common. So in TMCOMAS we are able to spray inner coatings. Laser cladding is much more complex. nowadays there are some guns, some cladding heads, sorry, that allows you to deposit some coatings in the inner surfaces. I have to say that in COMAS we have purchased one, so we are about to install it. That's why I have written here coming soon. So sooner or later we will have some inner coatings cladding head in COMAS also available for you. But it's more complex. Working place health aspects. In thermal spray, they are more complex. There is more fume, more sound issues, gas accumulation possibilities. So we will have we have to work with extraction, with gas sensors to avoid explosive gas accumulation. So in the practical side, the issues for health are more complex, while in laser it's quite simple. Just with a simple fume extraction, welding fume extraction machine, it's enough. Apart from eye protection, there are no need of gas accumulation and so on. So, well, safety requirements at the end in thermal spray is medium. So even that we have to use more extraction, soundproof booth, but at the end the safety is not so complex. It's only dealing with gases, with explosive gases, while in laser cladding the safety is dealing with eye protection and skin protection for the operators, which is more tricky sometimes. Okay. The final comparison slide is more about the properties of the coatings. In thermal spray, we can spray metallic coatings, yes. In laser cladding also. Ceramic coatings in thermal spray, yes. In laser cladding, no. Ceramic coatings, more or less, mostly tungsten carbide and chromium carbide. In thermal spray, yes, by HBF, for example. While in laser cladding, yes, but with a higher matrix content, okay, to allow the welding of the CERMET. CERMET stands for ceramic metal alloys. Polymeric coatings in thermal spray, yes. Laser cladding, no. The usual thicknesses in thermal spray, 30 microns to 2 millimeters, more or less. 2 millimeters is not for all materials. In ceramic and CERMET coatings, we are restricted to 0.5 thickness, while in metallics we can, and by flame spray or by arc spray, we can achieve 2, 3, 4 millimeters thickness layers, depending on the metallic alloy. In laser cladding is virtually infinite, so there's no restriction in thickness because, well, also depending on the feedstock material, no? In very hard materials like stellite or tungsten carbide or tool steels with a lot of chromium and carbon content, the hardness of the welding of the layer is very high. We cannot go very high in thickness, but generally speaking, with stainless steels, we can clad up to 10 millimeters or 20. But okay. Microporosity in thermal spray, we can play. We can adjust the parameters to play to have different levels of microporosity, but between 0.1 to 10%, I would say. While in laser cladding is 0. If the welding is correctly done, the porosity should be 0. Adhesion values 10 to 70 MPa in thermal spray, and laser cladding is virtually infinite because there's a welding. So the welding, the adhesion is the mechanical properties of the clad. So not infinite, but limited to the feedstock mechanical properties. Roughness after deposition in thermal spray is 2 to 6, 2 to 10, depending on the application, depending on the gun. And laser cladding, we are not spraying. We're not talking about roughness because it's just we have an as clad as well surface, which is not useful for any grip application. It's just ready to be machined, and that's it. We are not usually leave the surface as clad. Machinable or machinable coatings, in both cases, yes, and depending on the hardness, no, but even we can grind with diamond tools. So yes, more or less, in both cases, the coatings or the layers can be machined. And now it's time to start talking about some real use cases where I will try to explain you why we are using thermal spray or why we are using laser cladding, depending on the real case. No, so in this case we have a grey cast iron gearbox for a railway industry, and in these bearing houses there were some wear. So the bearing was not fitting properly in that seat. So we need a dimensional restoration of this area. So here the applied solution was a thermal spray coating by arc spray, thickness 0.5. Then it was ground. It was machined to array a surface roughness at 0.8. And we have used a stainless steel coating, okay, with a hardness of 40-45 Rockwells. Why we have chosen these thermal spray coatings? Well, mostly because we can spray inner coatings. It's an inner surface, as you can see here. It's easy to apply. The base material is not very weldable. It's a grey cast iron, so with welding we can have some problems. And especially because there are some restriction here for the application. The cladding head here will hit this part of the casing, so it's more easy to use thermal spray. That you can have an inner coating gun, which is like a tube, so it's easy to approach this area and so on. Okay. So the main reason was for spatial restrictions and base material issues. Another option, another example. In this case, the customer requests a high extreme wear resistant coating in reciprocating compressor rod or in reciprocating compressor cylinder sleeve. Okay, in this application, it's a it's an outer coating. In this application, is an inner coating. In this example, what was needed was a dimensional recovery of the sealing surface of the rod, while in this one the requirement was to improve the wear resistance in a new spare part. In both cases, the customer asked for a high wear resistant coatings, and in both cases we have some slender, high responsibility parts, easy to distort in case of very high heat input. So the applied solution was HVOF thermal spray, high velocity tungsten carbide cobalt chromium coating by thermal spray, with a hardness of 1,300 Vickers. Coating thickness was about 0.15 millimeters, 150 microns. Porosity 0.1, 0.5. It's HVOF, so porosity is low. Coating thickness must be kept low because of it's a very tough and hard and brittle coating. So we cannot go go for a very high thickness in this case. So why we have chosen HVOF instead of laser cladding? Well, in this case, because in this case it's clear, no? We have an inner coating and we don't have an inner cladding head. So the only way to clad this is by thermal spray. In this case, we could also have used the laser, but because our customer demand for a very, very high wear resistant coating, we choose thermal tungsten carbide, and the best way to apply a tungsten carbide with the highest tungsten carbide content is thermal spray, and that's why we choose in this case thermal spray. We could have also used here laser to clad with tungsten carbide coating, but the content of tungsten carbide in this case for laser cladding application is 60%, while in HBOF is 85 or 80% of tungsten carbide inside of the material. So the abrasion resistant, the wear resistant of HBOF tungsten carbide coatings is higher than laser cladding in this case. Different applications. In this case, the customer's demand for the electric coating, the electric properties coating. That means a ceramic coating. And if we have to apply a ceramic coating, we have to use thermal spray. While in this case here, it's a thermal insulator, thermal protection of this burner in the coal power plant. So also in this case, we are relying in a ceramic. So ceramic means thermal spray. And that's it. It's as simple as that. So the applied solution, thermal spray coating in both cases by APS, by plasma. In this case, as we have to apply a ceramic, we have to use plasma spraying because of its higher melting temperature. It has a more powerful flame, so it's able to melt the high melting point ceramics during the process. So we use the plasma here, atmospheric plasma spray. The thickness of the coating is 0.2, 0.3 millimeters approximately. And then in this case, it is going to be ground. In this case, we are going to left as sprayed because there's no need to have some precise dimensions in this burner. And for the electric properties, we are using aluminum oxide. And for thermal insulation, we are using zirconium oxide-based ceramics, okay? Hardness about 1,000 microns and porosity is higher because of the plasma spray. And in the case of thermal insulation, the parameters are set to create some porosity to improve the insulation properties of the coating. So at the end, the critical point here was the need of a ceramic coating, and if we need a ceramic coating, we have to concentrate, we have to use thermal spray. Another example, in this case, we had to repair a centrifugal compressor rotor, specifically the fitting area of the first stage impeller. We have removed the first stage impeller. The impeller was very worn, and it was some corrosion underneath the fitting area of the impeller. So we had to machine about 1 millimeter thick worn material, very corroded material in this area. So we need a very tough, a very soundproof, sound coating. So the best option here for us was to use the laser to apply a metallic coating. So yeah, we need a coating with a material resistant to temperature and corrosion, because this compressor rotor works in ammonium plant, so it was compressing some ammonium gas or something like that. So it was some corrosive case here, and also at high temperature. So the applied solution was to apply a laser cladding of stainless steel 431, which is a martensitic with 50% chromium, 2% nickel alloy. Thickness about 1 millimeter, 0% porosity, hardness. It was not so important, but this coating has a 50 Rowell C hardness, and then obviously ground to the specific dimension to allow the shrink fit of the impeller in this area. So here we could have sprayed by thermal spray easily, but we considered that as we have to shrink fit a 200 kilo impeller, we need a sound coating perfectly at there. So we prefer welding in this case. And what is the better way of welding using laser cladding. So because this part is quite critical, as you know, all these parts turn at 5,000 or 7,000 RPM. So we cannot deform the shaft by laser, by welding, by PTA or by MIG welding. So we kept the choice of laser to not distort this rotor during the welding. Another use case, in this case, we have a turbine shaft that was bent. I don't know if you are able to see here, but the bending in the ends of the shaft was about more than 1 millimeter. So the customer asked us to straighten this rotor, and we have used. We decided to make a laser cladding of all these journal areas here, of these shaft areas, to strengthening the shaft by cladding and then machining. So we have machined off all the seal areas in this area, and then we have clad the whole shaft. So we need for coating for dimensional restoration. We need for a coat or material that was resistant to temperature and corrosion. We need total adhesion in all recovered areas. And also we need in this seal area, we need a coating that could be machined to later on machine the seal surface profile needed. So the best choose here is, the best option is laser cladding. So we end up applying laser, stainless steel 431 again, in some areas 1 millimeter, in some areas 2 millimeters, and then we machined everything, we ground everything, we ground also the coupling areas here, conical one with some taper. So here in our case, we choose a laser for sure. It's a high responsibility part with the turns at 5,000 RPMs, and we need a sound and perfectly adhesion coating on that, while not distorting the part. So laser cladding was our option. Another turbine rotor. In this case, we need a dimensional restoration in bearing seat areas. These areas, in these areas, we need a perfectly well coating which resists well the support in the balancing machine. It might sound silly, but in very weight with a very high weight rotors, that has to be balanced after the reparation. If you repair the journals areas where the balancing machine should lean on by thermal spray, you have a very high risk of delamination of the coating. So the best solution is to weld. And if we speak about welding, the best option is laser cladding. So all the turbines rotor that we have repaired in COMAS, in journal areas, we are applying laser cladding to avoid delamination during low speed balancing. Okay, so yeah, the applied solution was a laser cladding 3-to-1 again. Is our workhorse of laser for turbine reparation. Thickness in this case was lower, so it's 0.5 millimeters and so on. So here, why we have chosen laser? To avoid thermal spray coating delamination during balancing. Yeah, it's simple as that. Another nice application. Now we are not talking about rotors. Now we are talking about a static part. We are talking about a thermal well protective cover. This is a static shell that it will protect the thermocouple. Okay, and these shells. This is I don't remember the name. The plate is the fitting of the thermal well in the tank, for example, or in the process pipe, while this part is in contact with the fluid or with the gas or with the liquid inside of the process. So here in this surface, the customers need that this surface, this cover material have to be protected. So the customer asked for a Stellite 6 coating. So we have a customer specification, Stellite 6, which is a cobalt alloy, because he needs for a coating resistant to temperature and corrosion. And we need of a total adhesion of all the recovered area, which is not only the tube, but also the face of this I cannot remember the name now in English, sorry. As you can see here, there is the part has a thin wall. It's a thin wall tube. It's not a tube. It's a blind tube. It's a thin wall. Okay, 2-3 millimeters. So just imagine now that you have to clad Stellite 6 by thick or by rod welding with in a 2-3 millimeters thickness tube. So you will have to stop, and you have a lot of risk of penetrating, of making a hole in the tube. So we are using the laser. We are using the laser also with a special device control that controls the laser power. So as soon as we have a heat input, as soon as this camera here detects that the melting pool is increasing because of the heat input, there is a reduction of laser power. So the heat input decreases to keep a constant dimension of the melt pool. So with this laser power control, we are able to clad from here to here, as you can see, is about 400 or 600 millimeter long tube. So we're able to clad from one point to the end without stopping and without making a hole. Thanks to this specially developed laser power control. So in this case, we choose to use laser because we need stellite coatings. The stellite coatings applied by thermal spray are not so good. There is some porosity. It's difficult to make a good adhesion of Stellite 6 particles because Stellite 6 is a material that is not affected by heat, so it's difficult to deform. So by thermal spray, Stellite coatings are not very well. It's better to weld them. And the best way to weld is using the laser. So in this case, we have used the laser. Another example of laser application. In this case, our customer had an actuator rod with a ACFE profile thread. It's a rod that has a thread machine in all the length, and it is used to actuate a valve gate. So the customer had a problem with the thread, and he destroyed completely the thread. And it has that's a breakdown of the plant during the weekend, and we have to repair the rod. It's a special steel, a heat-resistant steel. So we couldn't not find a new steel rod to machine it. So we had to clad. And we clad a stainless steel 410 because at that moment we didn't have any heat-resistant steel available at the workshop. So the only material that we could apply was martensitic stainless steel, which is also heat-resistant. So we applied a coating. We need a coating that could be machined. We must machine a thread in the coating. So the only way to do that is by cladding. We cannot machine a thread in a thermal spray coating. Is not welded. Is mechanically there. So there is no option to have a high mechanical property coating that will withstand a thread. So to machine a thread in a coating, you have to weld. So we use the laser to do that. Okay, so in this case, the thickness was about 4 millimeters, and then obviously we had to machine. So in this case, we have chosen the laser because the need of machining afterwards. The need of machining a thread afterwards. Another example. In this case, we have a customer that is crushing some grains, some vegetable grains to make some oil and some stuff. So they have some crushing hammers, some crushing machines with some hammers in it. So these crushing hammers now are made of 1.2379 steel, which is high-speed steel, 30% chromium steel, quenched 262 Rockwell C. Okay, and they have some wear on it. So they ask for a more wear-resistant coating to increase the life of these hammers. Okay, so we decide to apply thermal spray and laser cladding. Why thermal spray? Because the cost of application it was lower. It's easy to spray by arc spray some wear, some high resistant wear, resistant coatings by thermal spray. So we thought that with thermal spray, it will be a low price application, but also we decided to offer the customer a more high-end technology offer, which was by laser cladding. So we looked for a material that had a higher resistance to wear and to impact. So we end up finding a material that is available in wire to be applied by arc spray in thermal spray, and in powder to be applied by laser cladding. So the same feedstock material was applied by thermal spray and by laser cladding. Okay, we applied by arc spray with a wire fitting material. So we applied by arc spray an amorphous material with vanadium, niobium, molybdenum carbides, and so on. A very hard one, a thickness about 1 millimeter. So the hardness was about 70,000 beakers, can be 70 Rockwell C. And obviously we leave a sprayed finishing. There was no need to machine the crushing hammers, obviously, because there's no need to do that. It's just a hammer. So yeah, we did that, and after some hours we had the bad news of that some coating has been damaged. So we have some spallation of the coating here in the point. So due to the impact, we thought that the impact was lower due to the impact. We couldn't spray it by thermal spray. However, the laser hammer, that it has the same amorphous material with vanadium, niobium, and molybdenum carbides, about 1 millimeter in thickness, the same hardness, and obviously as clad. The same material applied by laser, it's still turning. So in theory, we have improved a lot. I'm telling you in theory because the hammer is still turning, so we don't have still feedback from the customer. So in theory, the life of the hammer has been increased by the use of laser cladding wear resistant coating in this case. So in this use case, we had the option to use laser cladding and thermal spray. Thermal spray was cheaper application, but due to the impact that was higher than we expected, the coating has failed. So there's only option to use a welding application. Okay. And this is the last, I think it's the last slide. In this case, we have used both processes, thermal spray and laser, to recover the same part. The customer has a piston pump which works with some pistons, and in that case there was a severe wear in the friction zone of the piston, about 3 millimeters, and it was a carbon steel piston, and also they had some corrosion underneath. So we had to improve the corrosion resistance of the pistons all together with the wear resistance of the piston. So we choose for a mixed combination, for a combination of both processes. We applied Inconel 625 for improve the corrosion resistance of the carbon steel piston, and then we machined the Inconel to the certain thickness to be able to apply APS aluminum titania coating by plasma. So at the end we had a base layer of Inconel 625 to protect the carbon steel piston for against corrosion damage. And on top of the Inconel 625, we had a ceramic thermal spray coating. We choose a ceramic because it has a high wear resistance. It is not so expensive as tungsten carbide, and it's enough for this application. So it's clear that in this case, the best option for a corrosive protection layer is laser cladding, because it has zero porosity, while in thermal spray we could have had some porosity. So the best solution for the corrosion resistant sublayer is laser, and the best option for wear resistant top coat is thermal spray, because we have to spray a ceramic, and the only way to spray a ceramic is by thermal spray. So this is it. Now is the moment to make some questions. Of course, you can always contact us by email or by phone. And the contact email is available on our website. And now we have some minutes for some questions using the chat. In any case, I will also share again my screen where you could see my email. You can email me for questions. Okay, there's something there in the chat. Let me check. Okay, is my colleague, the marketing manager, Raquel, that is telling you that you will find this webinar in YouTube channel next week. Okay. Let me remind you that we work with several customers applying thermal spray coatings and laser coatings to solve wear and corrosion and dimensional restoration problems. We are open mostly all the year, 24 hours if need. We are a good technological partners. We have a lot of knowledge on heat treatments, materials. We are able to help you for sure. Okay, it seems that no one has questions. I'd like to thank you all for your assistance to this webinar. That's it. Thank you for listening to me. I appreciate it. And okay, stay safe and take care. And hopefully we will see you soon. Goodbye. Goodbye.